Okay, so today we are getting together to talk about using additive manufacturing for castings of metal parts. Our technical expert today is Steve Murray, and I'll be moderating our event today. You can follow along audibly or feel free to participate using the chat. But before we go any further, I want to go ahead and introduce you to Steve Murray. Just a little bit about Steve. He has a degree from Indiana University in mathematics and is a journeyman pattern, mold, and model maker, registered with the U.S. Department of Labor since 1978. He's been using 3D printing in the support of the foundry industry since 1992, when he was employed at Elkhart Pattern. He's presented at the 2013 through 2017 Rapid TCT conferences, and he's presented, moderated, and been a casting track leader at the AMAmfg events from 2013 through 2018. In 2017, Steve was presented with AMAmfg's Dino Award for Distinguished Innovation and Operation in the Additive Field. And he's also been a trainer for AFS, for those interested in the use and implementation of 3D sand printing. He's a trainer and mentor within the foundry community about additive manufacturing throughout North America, demonstrating how castings are made with the foundry in a box to students from junior high and up through post-secondary students in engineering and tech schools. Please welcome Steve Murray. Steve's going to join us visually in just a second, but I want to get some basics here to go over with you real quick. We are recording our session. We will be accepting questions through the chat window. Go ahead and submit those. We will moderate those questions, and we may give priority to questions that have been asked by multiple participants. We're going to move along as quickly as we can to answer as many questions as possible, but we will stop accepting questions at about 12:55 to ensure we can answer those last few questions before we wrap up for the day. And so I'm going to kick it off. And Steve, are you there?
I am there.
Okay, great. Feel free to take over the video, and it's all yours for us to get started.
Okay. First of all, if you want to contact me outside of this event, please do. Heather will have my telephone number and email address.
Okay.
To give to you. Heather, am I hitting the right buttons? You
are visible.
Okay, good.
You're visible.
Let's get right down to it because everybody is brown bagging it and eating while we talk.
All right, Steve. Well, let's kick it off with our first question, which is, could you describe the process of casting for metal parts with just a brief explanation?
Okay, we are only going to talk about using additive manufacturing to make castings. And we're going to say castings by definitions are molten metal poured into some kind of mold. Now that can be either for investment or in traditional sand or any other kind of mold like rotating or you name it. But we're not going to be talking about printed metal. We're not going to be going down that path. We're going to talk about new technology, additive manufacturing, to make traditional castings. So it's going to be the new tool in the toolbox for making cast parts. And cast parts are traditionally referred to as near net shape. That means once they get done being cast, they're going to have some kind of post-processing. Machining, heat treating, you name it, whatever you want to call it, but not too many castings are being used straight from the foundry into as serviceable parts. The next thing we're going to talk about is what is the adoption rate for foundries using additive manufacturing? Well, it wasn't too many years ago, and I would say, it wasn't that many. Now, more than 95% of investment foundries are using, in one form or another, additive manufacturing, and the great number of sand foundries are using additive manufacturing where it makes sense. Now, a lot of this isn't broadcast. It's not talked about. Nobody asks how the sausage is made. Now, as engineers, you might be wanting to know what's the process you're going to use to make my castings. Totally legitimate question to ask. But a lot of the foundries are not buying the equipment to make these castings with additive manufacturing. They're buying the service out, just as they buy a service to make patterns out, or core boxes, or anything else that the foundry might do. The foundry is just where all these technologies come together to actually melt the metal, pour it, and get it out the door to the customer. So I think this gives us a pretty good basis to start our questions.
Great. Well, can you tell us which foundries are using additive manufacturing?
Most of the investment foundries are using additive manufacturing. They're using it for short run, and they're also using it where you would have a loose piece, a casting in a casting type situation where it would be difficult. Now, at what levels are they using it? It could be printing FDM, printing wax, SLA, PMMA, all these acronyms. It's just a different method of making your consumable pattern for the investment foundries. The sand foundries are using additive in gobs and gobs of different ways. They're using it, one, to print patterns, to compete with CNC cut patterns. They're using it to print cores. And they're then also using it to print molds in direct sand printing to pour metal into. So there's a lot of foundries using it in a lot of different ways. The real question is the foundries that aren't using it, where it doesn't, where they're ignoring the technology, sort of like a machine shop that doesn't have CNC machines. They're not viable, and foundries that aren't recognizing additive are about the same way. But it all depends on what the foundry's molding capabilities are, their processes and everything else, on how they use it. But most of the foundry industries in North America are looking at this and using it where it does make economic sense.
So piggybacking on that, Steve, what are the real benefits for using additive for casting?
The benefits are going to be greater engineering ability, better castings, faster, and cheaper. We're a long way from wanting to be in the foundry world to use something just because it's cool, right? Cool don't pay the bills. So everybody is using it to produce a better engineered casting, better quality product, faster to the customer, quicker turnaround, and because it is cheaper. Now let's just delve into that a little bit more. The faster to the customer. How is that possible? You don't have the intermediary of making tooling. Having that whatever number of weeks or months to wait for tooling to get made. In the sand world, it means printing molds directly, and then they go to the foundry and get poured. No more patterns being made. It's also quicker to the customer because the engineering folks don't have to take the model or the design and start cutting it up to put draft on things so they can make the tooling. Remember, just because you design it doesn't mean it can be manufactured. And additive, in the way of printing, makes things a lot more manufacturable. Now, there are certain traditional rules of physics you can't overcome, but you don't have to spend all that time to decide how the pattern is going to be cut, divided, and so you can pull sand off of it. Traditionally, the patterns are relatively easy to make. It's when you get complex cores, the internal systems inside of a casting, that things get very, very complicated. Those would be where you're having a dozen or even multiple dozens or hundreds of pieces being put together like a Chinese puzzle to fit inside the mold package to be poured. With 3D printed sands, that assembly time is taken away and the human error of those assemblies is reduced.
So Steve, when looking at, trying to start using or trying additive for casting, when is a good time to start implementing that?
Right at the design aspect. We're not designing things now for traditional. The new design aspect is we're trying to make things that have never been made before.
And
make something engineered for collapsibility, for added strength, reduced weight, all those kinds of things.
So really focusing in at the engineering level.
Yes, it starts there and works its way down. If you design parts now that cannot be made with traditional casting methods, you just might be looking at you have to use additive manufacturing to make that part. So people might say, well, is it more expensive to make that? Well, it might be expensive, but the alternative is you couldn't make it at all. So it's opening an area where we're going to be able to make metal castings that were never thought of before being made.
Well, what are the different metals that are being used right now for casting, and what about like composite metals?
Composite metals, in the foundry industry, we call composite metals alloys. And there are literally books and volumes of books with the different alloys of all the different metals. The aluminums, the bronzes, the steels, the irons, all have literally hundreds and hundreds of formulations for these composite metals that we call alloys. And in additive manufacturing, anything that is being cast now can be cast using additive manufacturing. There is no restriction or reduction of the number of alloys that can be molded, cast, and used.
What are the main metallurgical challenges when using additive?
Those are going to be a lot of the ones that are facing the engineer with the new designs. You're able to now design things that have physical shapes, topography that were never able to do before. Things that go back on themselves, thin sections. These are the restraints of how do we do that, and that brings in where solidification analysis, flow analysis, all these simulation softwares come into play. There are so many out there that as an engineer, that before you go to the foundry to want to get something made, all these things should be checked out and not leave it to the foundry to say, oh, we can't make that. You have to figure that out beforehand. You get so much work into this. Well, just as a personal note, my job for many years was to be the Grinch. I was to tell the engineer, hey, that's a great part. Sorry, we can't manufacture it. You have to go back and redesign because of this, this, and this. Now with solidification and simulation software and flow analysis and all the rest of these tools that are on your desktop, you can get to where you're 85% sure you're going to be able to make this before you even submit that that design to the foundry. And the thing is, you can try multiple answers to your engineering problem with your casting design all simultaneously. So if you have 3 or 4 good solutions and you want to try them with 3D printing or additive manufacturing, you're able to try them all because you're not investing in tooling. It can be done in real time and happen just as quick. It isn't one or the other. It's you can just speed through this process.
So what is the biggest hurdle additive has to overcome for further adoption in the industry?
Most likely it's going to be price. That's the thing that's driving things. For the longest time, we didn't have much competition in the industries of additive manufacturing, and prices stayed high as what the market will bear, and not to what things were, let's say, worth, if you will. With more people coming into the market, let's say patents coming off of things, other people wanting to get in the game to play, they're reducing the costs of materials, of machines. We have now universities that are offering education in these subjects. So we have a workforce coming in that is ready to go. You know, Heather, that I don't have a dog in the fight. I'm not getting paid or promoting any certain product, company, any of the rest of that. So when I'm throwing out examples, that's all they are. That's all they're meant to be. But as for education, the University of Northern Iowa is doing a tremendous job getting young people ready to go into the foundry using these new technologies. we've only had a few big players for printed sands, silica, and now we have more people coming into those um, to make more and different machines to drop the price to get it so this is commercially viable. Now, when it comes to large-scale manufacturing of these, I'm always asking the question, what are you considering large scale? Um, you know, for automotive work, it, what is it, 150, 250,000 units of something? For aircraft, is it 250 or 300? So large scale production for different industries takes on different amounts. And I know that there are many additive pieces going into parts that are just under the 100,000 units a year capability. So that is large scale production in my book. But it's mostly, is the need being met, and is it price cost effective?
So what would be the best materials when you're talking about 3D printed pattern making?
Wow, that opens a whole realm of things. The best materials for 3D printed patterns, you would have to ask the question, what is the foundry process being used? And then try to match the material to the foundry process. So if you're having a foundry that's horizontal parted or vertically parted, or if you have a foundry that is doing air set, or let's say a foundry that's doing something with large castings where the smallest thing they pour is 5 tons. All these things influence what the material for the patterns will be made of. Traditionally, we set patterns up and we would cut them on a CNC machine, or before that we would use wood and cut it, shape it, and glue it together, make patterns and core boxes. CNCs took that and made it by a factor of 10 quicker, with setting up a big block of material and just letting the machine run 24/7, cutting it away to make the shape you wanted. Well, now we have the ability with machines, for example, BAM, to lay down material just what's needed to be machined away. So you're not wasting as much material and hence quicker. Plus, you're having a machine essentially glue up your pattern so you don't have to have labor doing it. A lot of these patterns we're trying to get reduce labor cost, less man hours, if you will, in making them. Doesn't take away the design time or any of the rest of that. Let me get a little sip of water here.
While you're doing that, let me ask you about existing applications for printable resin in lost wax casting. We have someone who's interested in the material density requirements, burnout cycle requirements. What can you tell us about that?
All of the 3D printed materials for the investment foundries have specific burnout requirements, and the manufacturers of those chemicals can give you the information for your foundry to do that. Excuse me, I'm just getting over a head cold. Um, the investment foundry burnouts and all those materials that are used, a lot of it depends on what you're trying to make in the way of a casting. You pick different materials for different topographies, if you will, to make your casting. These are tools, and you have a toolbox, and these are a new set of tools, like a whole new drawer in your roll-around toolbox set. It's just not a hammer and a wrench. Now you have all kinds of things and a wide array to pick and choose to help you make the casting the best possible that it can be. Hopefully that got into some of that, and if not, we can talk about it later offline.
What is the maximum dimension casting process that Additive will accommodate?
Well, we're going to go on to two extremes. We can go as large as what can be poured. So the printed silica sands can go together like Legos and produce things that are many feet and many tons in size. And then with investment foundries, with the printing of materials, we can go very small as well, thimble size, if you will, or smaller.
Okay. How can we drive better surface finish on additive assisting tools to reduce the need for post-processing on the casting parts?
By definition, all castings are going to have to be machined because they're just near net shape. But some of the unwanted layering of lines that is inherent on 3D printing can be helped and controlled by the orientation of the part into the print volume. Put critical sections more parallel with it for that kind of thing. And then with SLA and some of the others, it's laser resolution, and those can be essentially very good. A lot of your fine jewelry is now being done with 3D printing and castings. So remember that the gold earrings and brooches and rings are made in a foundry.
So we have someone who asked about the dimensional accuracy, roughness, surface quality, and finally designing the part to be used in additive manufacturing. They're interested specifically in SLM.
Let's see. The dimensional accuracy for a lot of printed pieces that are going to the foundry are very accurate. Remember, they have to compete with CNC produced parts or molded parts. When we have different media that is being printed, let's just start off with silica sand. If we're printing sand, silica sand, you're not going to be able to get anything a finer resolution than the grain of sand size. So you're going to have this natural roughness, if you will. Going to be like sandpaper, maybe fine sandpaper, but still sandpaper. And if we're printing with other materials, waxes or FDM or some of these other materials, they're going to have their own unique properties on smoothness and dimensional accuracy.
So what would be some of our current available standards for measuring?
Our way of measuring a lot of this is going to be with touch probe or with laser. With touch probe, you did traditional checking of parts at certain places, and with lasering, we're able to check the whole part and that kind of thing. Some of these do have issues in that you can only check what you can see. So if you're going to check things beyond that, you're going to have to use some form of X-ray or other measuring tools.
I think we kind of just touched upon this a little bit, but the question we have is the SLA finish smooth enough for sand casting? And I just want to make sure we've kind of gone through that specifically.
SLA definitely is smooth enough for sand castings. If you need it a little bit smoother, let's say because your SLA is rough because of your laser focus, well then a minor touch-up of sandpaper or a painting. Putting on a thermal barrier also helps it last longer in the sand. Because these materials that come out are heat sinks. They'll take the heat from the sand and absorb it and not readily give it up. So you could end up with these plastic materials that are going to be in the foundry for sand getting warm to the point that they become non-structural. They become loosey-goosey, rubbery, or they start getting grabby with the sand. They don't release well.
Those are the technical terms, right, Steve?
Yeah, loosey-goosey, yeah. Okay. Now, another really cool way of solving that problem is to electrocoat them. Put a metal, vaporized metal coat over them. It reflects the infrared and it makes them super smooth. And then they last hundreds or thousands of hits in the foundry if needed.
So someone's asking about how do you ensure the geometries made with additive to make the cast produces a part that can easily come off the cast?
One more time, please.
Sure. What can you do to ensure the geometries made with additive to make the cast produces a part that can easily come off the cast?
Okay.
Is that one a better offline conversation?
It might be, because I'm having a hard time just sort of wrapping my head around that one. I'm sorry.
Sure. Well, we'll follow up with the person who submitted that question and try to get that answered for them offline. So moving along then to the next question, can you use powders to do casting, or are you just pouring metal?
The powders for the castings A powder would be like the silica sand, or you could use ceramic powders for printing what you're wanting to make your casting from. But we're not talking about printing metal or powdered metals being used. That's not, the topic of this conversation.
What are some brand name of 3D printers that are commonly used right now?
Oh my goodness.
We don't have to list all of them, maybe just.
Well, in no order of importance or preference or anything else, um, VoxelJet makes a sand printer, and a PMMA printer. X1 Corporation makes sand printers. Um, we're talking industrial machines here um, for castings. 3D Systems and Vision Tech have some. There are just realistically too many to talk about. There's just a host of them. You'd really have to know what you're wanting to do, um, the process that you're looking to use, uh, because there's such a wide variety. You can buy something that you couldn't use for the process you have, and that would be a terrible situation. Um, so, you know, we're almost at the place like car companies. How many different cars or trucks are there? And that kind of thing.
So you need to just be very cognizant of what you're trying to do and find the one that's going to work best in that
Yes,
specific.
and ask the questions to people in the industry. If you're wanting to make sand castings of iron parts, that would steer you in one direction as opposed to making magnesium castings for aircraft. That's another whole thing. They're totally different. Or if you're making castings that are for medical instruments, it's such a spider's web, if you will. We're starting at the center, and you can go in just about any direction, and they won't come back. They just go off on different tangents on where you want to go.
So besides saving time, what are the relative percent cost savings using additive for casting, maybe in a ballpark?
Well,
And we're talking estimates, right? So this isn't
estimates. To the savings for investment castings, let's say, if I got the order today to make some castings for someone, we could have printed patterns at the foundry in 4 days. No tools, just go ahead and print them and get them to the foundry. If we were going to make a tool to make the patterns, that could be anywhere from 4 to 6 weeks. Those kinds of savings are not in days, but in weeks, or even sometimes months. In traditional sand casting foundries, it's getting to the place now where that if you have more than 4 core pieces to go together to make a casting, you will not put those cores together or make those cores separately and have a man assemble them, or a person. You will go ahead and just print the core without any tooling, because you're getting consistency of build. the accuracy, and you have savings from that in that your fallout on scrap rate goes way down. Uh, there's examples of in foundries where you had, over 60 core pieces being assembled, and there's only one guy, Mike, who knows how to put those together. And if Mike's out sick or on vacation, you don't make those parts. And if the customer really needs them, well, you got to wait for Mike. Uh, this way, you have that ability to make these cores, have them already pre-assembled into a core package and sitting on the shelf. And there is no usage date on these. They can sit on the shelf for quite a while until they get damaged, in the foundry itself. We have these things and these abilities, and it's how do I put a cost on those? Now, when you're making a core in the foundry, you're blowing sand into a box. To get the sand to go into the box, you have to put a place for the air to leave. So the air is carrying the sand into all these little crevices and nooks and crannies, if we will. You do that with a vent. You do that with putting a way for the air to escape, catch the sand, air keeps going through. See, that's one of the beauties of sand, is that it is porous enough to let air out, which means that when you pour molten metal into a sand mold, the gases, because of the increased temperature, can escape through the sand walls itself, but they're close enough to hold the metal in. So, that being the case with your cores, you could be blowing sand in, but not getting the compaction that you want. You're going to have spongy areas, soft sand that is brittle and breaks off, and that means you won't get that definition on in your casting. And you don't find that out until it's already machined up and you're going through all these processes. With the 3D printing of those, you're getting a consistency of density of your build and an accuracy. All these things take the scrap rate in a foundry way down into the machine shop, post-processing. All these things that knock out your parts that you put labor into and money and can't sell, or they have to be reworked, all those things have dropped down. And these are on the factor of 10 or more. People are finding this just makes economic sense. The other savings is on legacy parts. Let's take, for instance, our nuclear industry. Most of our nuclear plants were one of a kinds. All the castings and toolings for these pumps and valves and all this other stuff were custom made. Well, as they reach the end of their life cycle, you have to make these things again to replace them. Well, instead of starting out with tooling and have to go through all that process again to make one of something that you won't need a replacement for another 25 or 30 years, you could go ahead and just 3D print these things. So it's not just the nuclear industry, it's the pulp paper industry, the oil and gas, the petrochemical, the pharmaceutical, you name the industry, they all have these custom machines and plants and industry parts that were made just for them.
So there's really a lot of different aspects that are impacted that can affect your overall cost savings,
Yes.
short term and long term.
Yes.
Okay. Can you talk about the capability of using conformal cooling in cast molds and tooling?
Yes. Conformal cooling is instead of having just drilled lines plugged to heat and cool a mold, we're talking about having it follow a path that is more, I don't know if ergonomic is the right word for it, but if you think about like the blood vessels and veins in the body, or the veins in a tree leaf, they're all by nature set up in these organic ways to find optimization of transporting of, let's say, a fluid. Well, we can adapt these very intricate methods into now our moldings, our parts that are going to make either plastic parts or other metal parts, and put them in there with additive manufacturing. And they reduce the heating and cooling times and give better product and longer life to the molds themselves.
Can you shed light on lightweighting, specifically thermal management, and adding complex features? There's a few different things here: part consolidation, assembly, fit up, quite a bit in this one question. But can you touch base on a little bit of that?
Sure. Wow.
Maybe let's start with the lightweighting aspect.
No. Okay. Well, we can. Well, we'll just start, and you just interrupt me and tell me when we go on to the next one.
Okay.
Part consolidation. Many things are made the way they're made because that's how we make things. I know that sounds stupid, but you might design in engineering a component, but you can't manufacture it, so you break it up into different pieces so you can manufacture it. When the manufacturing methods change, suddenly you don't have to break things up, let's say. You don't have to make multiple parts and put those sub-assemblies together. It would mean less joints, less machine time. You think of all your pipes and ductworks. You see it in your home, if you will. Think of your plumbing fittings. You have an elbow because the pipe makes a turn. Well, what happens if you had all one piece? You wouldn't have to put an elbow on. That's where, like, a rubber hose can bend around a corner. So you take the same thing in with castings, where you have turbochargers, heat exchangers, manifolds, all these things that would be better if they only had one piece, so there would be no gasketing, no need to have them split apart. Well, if you can do that, then your cost of manufacturing goes down. Your cost of warranty goes down because you're not having another place where something can go wrong, have a leak, break, or have issues. So all that kind of stuff is great. Light weighting. There are a lot of things that we manufacture in the aircraft industry in the way of castings that have an awful lot of material on them, and we put them on there, the material on there, so we can make it, and then in the machine shop they have to machine it all away to get to the right weight, if you will. Well, with additive manufacturing, we're able to say, okay, we're going to get it closer to that shape. You don't have as much machining. And then another part of lightweightness is that we are able to have engineered products that do the same amount of work, if you will, if they have the same engineering specs and they weigh less, because we have put all the emphasis where it is needed for the engineering. And it's just not big, bulky, and heavy because that's the way we've always made it. We just put the mass of metal where it is needed. And that is another form of lightweighting that is happening. And it's all in the engineering, starting with that. It sort of goes back to what we started talking about in the beginning, how engineering of these parts, and as engineering come up with new and better things, additive is there to assist them in the manufacturing.
So we're getting really close to the end of our time together, and so I just want to take a quick second to put up some general information that I think would be helpful to have for everybody as we are getting ready to wrap up. Just for those who are still on the webinar with us, thank you for hanging in and waiting to get your questions answered. I know we do have a few more questions we're going to go through, but there will be a survey once the session's over. We just ask you to please share your feedback with us because we want to improve the series and make it more applicable to you. If you have questions for us or follow-up, you can send them to us. Or if you have suggestions for upcoming topics and speakers, feel free to email us at AMAmfg@sme.org. And we're going to have some upcoming webinars. Not all the dates and speakers are finalized yet, but be on the lookout via email for some updates with new topics and speakers. And we're also planning to have some live speakers sharing information and having face-to-face at CMTS in 2019, which will be September 30th through October 3rd, a little bit later this year. So stay tuned for updates on that. I know we had a question about getting Steve's contact information out there. I will make sure that we get some information from Steve and make it available so that you can follow up with him if you have additional questions. But again, feel free to pass along your questions to AMAmfg@sme.org. We'll get them to Steve. And if you include all your contact information, he can follow up with you if he has additional questions or can get back to you directly.
If anyone wants to call me, my phone number, and it's area code 574-210-5934. Don't call me from a blocked number because if it's blocked, I will not be answering it. This is my one and only cell phone, so you and my grandkids are calling me at that.
Uh-oh, Steve. Open the floodgates. You're going to start getting...
No, it's fine. That's what, it's all about making connections, and if I don't know the answer, I'll pass you on to someone who might be able to help you. And then my email is 5934murray@gmail.com. And I will try to get back with you or lead you to where someone can help you. This is all about you know, progressing our industry, our trade further, and helping everyone get just a little further up the ladder. Uh, my time in this industry is short now. I'm an old timer. In fact, I'm going to be playing Santa Claus next year. See this? That's what it's for. Um, and I want to help other people catch up and do better and make better things. The idea of things that we're going to make, I can't imagine. So keep designing, keep making, keep going
Well, Steve,
forward.
thanks for providing your contact information. We'll have that offline as well so that people can reach out to you with their follow-up questions. But we do still have a couple of questions. If you have a few more minutes, we'll
Sure.
go ahead and go through those. Again, we're recording this session, so if we'll have it available, we'll let everyone know who registered and signed in. We'll let you know when that recording is available. So if you had to jump out at some point or you missed the beginning of the session, you'll be able to go back in and watch that recording later on. So a couple of our last questions here are related to precision. Specifically, how precise can 3D printed sand mold be?
Wow. Printed molds can be, hate to say it, it's about like depends. I hope I never have to wear those. But depends on the size. We're able to make things in the range of a microwave oven, printed stands, um, about as accurate as an investment casting, traditional investment casting. We can make other things, big things, um, something that is 12 feet long, 12 feet in diameter, um, as accurate as what we can set the sands, which is probably a 64th of an inch. Um, the accuracy of the molds is incredible. This is the thing that is mind-boggling. You've taken the human error out of molding and ramming and everything to make these things to now it is machine made. That was never possible before with uniform densities, and you'll be able to predict shrinkages and your casting outcome because of that repeatability. Now, if you're asking, is it going to be accurate the first time out of the box? Maybe not if it's never been made before, because you have to get that continual feedback of what you're putting in, what you get out, readjust your formulas, and go from there. That's, needless to say. So you have to be ready to learn and use what you learn to do continual improvement.
So a little earlier we talked about tools for measuring accuracy, but what are the specific standards in place right now related to accuracy?
Are we trying to get the ASTM standards for accuracy? That's what I'm trying to understand that. Are we trying to get what is our methods of what are we measuring of these things? Is it how we're measuring, or is it what are we measuring? Let's just take for example, you're printing out a sand mold out of silica. You're going to measure the overall dimensions of whatever it is that your mold is. You're going to measure your density of sand. You're going to measure the amount of chemical binder that is used to hold the sand together. You would use for that loss on ignition, process. Um, if you're 3D printing something for the investment industry, you would have to check it to make sure that whatever you've printed is watertight, that it would hold a vacuum, because when you dip it in ceramic, if it wasn't, some of that ceramic would leak inside and cause a defect. So that's what I'm trying to understand, is what are we talking about on the measuring as opposed to how are we measuring? I don't know if I'm making myself clear.
That's okay. I kind of get where you're going, but I think we don't really have any more details from the person asking the question. So
call me, have a conversation. Yeah.
Yeah, maybe they'll follow up with you directly and can get some more details from you on that. But it looks like our final question was submitted, and that is, what 3D printing method and material is best for investment casting A356 aluminum alloy? And the price was about 5 pounds.
The best printed pattern for that is the one that the foundry wants, that is casting that alloy. Different foundries have different likes and dislikes. You don't have to worry about antimony in any of it, so you're wide open. As far as I know, that it's what the foundry would prefer, and I am not going to try to dictate anything to a foundry because they're an independent sort, and they know what they like, and that's what you give them.
Oh, okay. So our question, the person asking the question said, what if they have never done this and the foundry does not know?
Call me, and we'll get with the foundry and we'll find out what their burnout procedures are now, and then we'll get them something that is very similar, so they can do that. We don't want them to create anything new. We just have to fit to what works in their schedule. There are so many variables that you can't throw out an answer for that. I know it's a bad analogy, but I'm a plumber. What kind of pickup truck do I need? It's like, come on. You can make any pickup truck work if you're a plumber, or panel truck or whatever, but it's, what do you prefer? This is the same thing with the foundry, is finding out what their idiosyncrasies are, how their processes work, and then find something that'll match with it.
Well, I think that's our last question for today. I know we went a little bit past our 1 o'clock time frame, but I think having those few extra minutes helped us answer a couple extra questions. I want to just pull up our last slides here just as a reminder regarding the email address that you can email us. We have in the chat window Steve's contact information so that you can follow up with him if you would like to do so directly. And we just want to say thank you for attending. To everybody who signed on earlier, who's still with us today. Thanks so much to Steve for taking the time to answer your questions. We look forward to seeing you at another AMA MFG coming up soon. And we're done for the day. So thanks so much, everybody.